Hello, I've got a couple questions about the problem on this page, and I thought I would just take a second pass at solving it for anybody who may have been stuck on a couple aspects of, I'm just going to zoom in here on this problem. So we have a mole of oxygen, and the fact that this is a mole is really not part of the problem, but we have 32 grams of oxygen in a container at room temperature. We're given the average velocity of the particles is 1,080 miles per hour. We're asked to determine the kinetic energy of the particles in joules and kilojoules. And a couple of things here. One would be that kinetic energy is just related to 1/2 mv squared. So the mass of an object times its velocity squared times 1/2 is related to its kinetic energy. So any particle or any object in motion at some velocity will have kinetic energy based on this equation here. Now, if we want to convert to joules, the proper conversion to 1 joule is that 1 joule is 1 kilogram meter squared per second squared. And so when we start thinking velocities in miles per hour, we're going to want to transfer these over to meters per second. So we can square meters per second and get the proper units out that we need the energy unit to be in to convert to joules. Okay, so the first thing we might do in this problem is just kind of convert grams to kilograms. So the object's mass in kilograms would be this number of kilograms. And again, I'm just going to convert to kilograms for later use in converting over to joules. And then I'm also going to convert my miles per hour to meters per second. The number of meters per second in 1,080 miles per hour is, a conversion we need to do. If you have to do this on a test, we would give you these conversions. We'd say 1 mile is 5,280 feet. We'd say 1 foot is 12 inches. We actually write out an inch explicitly. 1 inch is 2.54 centimeters. And all these conversions are exact. All these conversions are exactly defined. So we probably wouldn't give you the hour in a second. I think we'd expect that you would know that if we want to go to meters per second, 1 hour is 60 minutes. 60 minutes is 60 seconds. So that's 3,600 seconds. And then we would just do the conversion over to centimeters and ultimately meters. We'd expect that you would know 100 centimeters in a meter. So we'd expect that you could convert here 1 mile, 5,280 feet, 1 foot, 12 inches, 1 inch. I don't know why I put this with the ones, but 1 inch, 2.54 centimeters, and 100 centimeters, 1 meter. And if we do these conversions here, do 1080 times 5280. Oh, I forgot to divide by 3,600. Not that it matters, but 1080 divided by 3,600 times 5,280 times 12 times 2.54, and then divide by 100. So it gives me 483 miles per hour, or 483 meters per second. So mile cancels, feet cancels, inch cancels, centimeter cancels, we get the meters, then hour cancels, we get the seconds. So we get our intended units, meters per second. And so then to solve this problem, our kinetic energy would be 1/2 0.03200 kilograms, and then times 483 meters per second squared. That's going to equal 3,730. Now joules, because that's well, let's write this out more explicitly. This would be 3,730 kilogram meter squared per second squared, where all of this here is the joule. And then we want to go to kilojoules. 1,000 joules per kilojoule is 3.73 kJs. I'm at the edge of my screen. I move it over. 3.73 kilojoules. Or the kinetic energy that this collection of oxygen molecules has in this container at whatever this temperature is. So by virtue of these particles being in motion with a particular velocity, allows us to calculate their kinetic energy. And you can see this is actually pretty small. Or at least when you start thinking of, bond strengths, how strong chemical bonds are, this is, a lot smaller than the strength of a bond of a molecule. So predominantly, when we think of chemical reactions taking place, it's the breaking and forming of bonds. They're going to have a much greater change in potential energy compared to the changes that their potential energies might have, or their kinetic energies might have, by virtue of the particles moving around their containers. So just an introductory example on how you can think of kinetic energy for a gas sample, seeing, or maybe appreciating this later, but hopefully later appreciating that this is a really small amount of energy compared to the potential energies we might have for chemical reactions that can ensue if we start breaking or making bonds throughout the course of a chemical reaction.